Alright, so I picked problem 30 because it's sort of similar-ish to one of your, I think, quiz problems or test problems, but also because it has both x and y directions for force, but it doesn't use the perpendicular distance thing that I showed you last in problem 24 because it's already set up so that the distances to a pivot point are already perpendicular, so you don't have to really use sine or cosine for perpendicular distances, although you will need sine once in the problem. So, alright, so let me just draw this real quick. So we got a wall. And a hinge. And a bar, perpendicular bar going this way. And a cable. Or a wire, it says in the problem. A wire. They give us the angle, so it's theta, and there's a block on here, a distance x. Yeah, the length of the bar is L, and they give us, the weight of the bar, so W bar, and the weight of the block, we'll call that W. Let me make this longer, just it's easier to draw, less cluttered. W block. Alright, so that's good. And yeah, so we might as well list the other forces. So the tension acting on the bar here, the uniform bar, it's going to have a y component pulling up, so we'll call this Fty, and it's going to have an x component pulling in towards the wall. So let's draw that here, I guess. Ftx. The hinge is going to, because this bar wants to, like, gravity's pulling on this end of the bar too, right? So the hinge is going to keep it from falling down, so that's going to act up. F, we'll just call this Fy. We call it F hinge Y, but just save a letter. And of course, the wall is going to push the bar back this way because tension is pulling it into the wall, so it's going to counteract with an Fx going that way. So might be a little cluttered, this drawing, but you can pause the video and make sure you understand everything I drew on here. I don't think I missed anything. Looks good. Let me just list the givens here. L is 3 meters. The weight of the bar is 200 newtons. The weight of the block is 300 newtons, and the angle theta is 30 degrees, and T max, force tension max, is 500 newtons. Let's define up as positive, down as negative, the usual clockwise positive, counterclockwise negative. And yeah, so let's do Fnet x and y. So Fnet x we'll start with. That's going to equal 0 because it's in equilibrium as always. And so Fx is to the right. that's positive, minus ftx to the left, and that's it. Let's do f net y. Up forces, we got fy and fty. Down forces, we got weight of the block, and also down is the weight of the bar. And we know those, so might as well just, whoops, and that equals 0. So 0 equals fy plus fty minus 300 minus 200. While we're at it, we can actually, based off these this angle, we can figure out what ftx and fty are according to the maximum tension. So let's do that. Opposite is sine. So sine 30 equals fty over the tension, max tension force along the hypotenuse that way. It's going to be 500, so this is over 500. So fty equals 500 sine 30. And accordingly, ftx, which we don't actually end up needing, ftx is 500 cosine 30. So we can actually say 0 equals fy plus 500 sine 30 minus 300 minus 200. And that allows us to solve for fy. So fy equals 250 newtons. That's nice. Yeah, anyway, so now let's do net torque. Torque net equals 0 equals. Now, where to make our pivot? Well, we're trying to find x, the maximum possible distance before the wire breaks. So you can probably see, or intuit with your intuition, the farther it gets along here, the more the tension's going to be, right? Because the rope has to support more and more weight. And so once it reaches 500, what is the value of x? You can see, like, if this is way over here at the wall, then at the actual pivot, in a sense, then there will be no weight pulling down the bar, so the tension wouldn't have to support this. And so Tmax would just be due to the weight of the bar, not the block as well. So whatever, that's obviously got to be less than 500, or else they probably would have picked a different number for Tmax. So let's say maybe it was like 200 or something over here in newtons. So then as x increases, this tension is going to increase up and up until it reaches 500. And then snap. So anyway, where to pick our pivot? Well, things we don't want to pick it at. We don't want to pick it at this block because first off, the block is moving. It's not in a fixed position because we don't know what x is. X could be anywhere along here, so we don't want to pick it at the block. Other than that, my first choice, which worked, I didn't really have a super good reason except that I just looked up here and I saw, like, fy, no, ft's. Let's pick w bar. I really didn't have a good reason, honestly. So my gut just sort of told me that after doing enough of these problems, you sort of get an intuition for it. Not to say that other pivot points wouldn't work. I didn't try them, and unlike problem 24, I'm not going to try them in the middle of the video. So I'm just going to stick with making the pivot at this point. So by doing that, first off, you should be able to see that fx and ftx are not going to rotate the bar, because they are parallel to the bar, and so there's no way that they can rotate it. If you're going to rotate this bar up and down, you need at least some sort of vertical component to your force. So we don't even need to worry about those. So now, if this is our pivot here in the middle, then Fy is going to rotate it clockwise around this pivot point. Fty is going to rotate it counterclockwise, and the only other force is the weight of the block. And currently, if it's on this side of the pivot, it's going to rotate it counterclockwise, so we'll make it negative. But as you'll see, the distance from the pivot will take care of whether it's on this side negative or on this side rotating it clockwise and it's positive. Alright, so let's do this one first. It's pretty easy. Fy, how far is it from the pivot? Well, it's L over 2. That's easy. And then this one's pretty easy, Fty, but it's minus, so Fty, which we know, by the way, is that. How far away is that from the pivot point? Oh, it's also L over 2. Yay! And then currently, if I have the block over here to the left of the pivot, it's going to rotate it counterclockwise, so that's negative. But again, and by the way, this is W block. How far is it from the pivot? Well, it's this distance. It's not x from the pivot. It's x from the wall for the hinge. So it's this distance. I'll just call it question mark. What is that distance? Well, it's L over 2, this distance, minus x. So when x is smaller than L over 2, meaning the block is on the left of the pivot point, then this becomes positive, and this stays negative, and it rotates counterclockwise. If x is larger than L over 2, so bringing the block over here, x being larger than this makes this negative, which makes this positive, and if that's positive, that's a clockwise rotation, which should make sense because the block being over here is going to push down on this side and rotate it clockwise. So it takes care of both cases. Alright, so from here, we know that, let's see here, 0 equals, so Fy is 250, we know that, 250, L is 3, so L over 2 is times 1.5, minus Fty, that's 500 sine 30. Suppose I could have done that out, simplify that. L over 2 is again 1.5, and the weight of the block is 300, and L over 2 is 1.5 minus x. Hey look, x is our only variable. Because we saw for Fy earlier, up in the net force equation. Notice we didn't technically need the F net x. I just wrote it just to be complete, but we didn't need it for this problem. Anyway, solve this for x. Just a wee bit of algebra, and you get what? X is 1.5 meters. So when the cable snaps when the block is right over the center mass of the bar. Interesting. So the book picked a interesting number for that. Had they picked a higher number, the block probably could have gone over here before the rope snapped. So that's a cool problem. We didn't need the R perpendiculars because everything was already perpendicular to the pivot point, but we still needed to write out F net x, F net y, torque net, even though technically we didn't need F net x. We still had x direction forces. So. Alright, good problem. And that's all I'm going to do for sample problems. That should be enough to get you going through all these. And let me know if you need anything.